11.3 probability distributions. So probability distributions just shows you all the possible outcomes of the thing you're talking about. So like in here, they give 2 examples. If you roll 2 dice, right, what are the outcomes? Well, you can get any number between 2 and 12, where 7 being the most likely, and then 2 and 12 being the least likely. Over here is miles per gallon. So they took like a survey of cars, and they got, wow, on average, most cars got 24, some of them got 18, some got even less than that, some got 30, some got even more than that. Now, if you notice though, these are very different. This is a strict amount. You could be 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? We can't roll 2 dice and get 3.5, for instance. You can't get 8.1. It doesn't work that way. Miles per gallon, you can though. You could get every number in between. You could get 21, you could get 22, you could get 19.1. You could get any value in between. We have names for these two. The one right here where it has to be certain values that fit in between, we call this discrete. Easy way to think about it is this is the ones you could count. You can count the number, you can count the values on the die and all that stuff. Right here we call this continuous. This one it's like a measurement. Continuous data is anytime it falls in between. So like miles per gallon, does it have to be 1821? A good way to think about this is the size of your feet. Right? It could be anywhere. Like it might be a foot, it might be 8.5 inches, it might be 9.3 inches. But discrete would be shoe sizes. Right? Shoe sizes come in 7, 7.5, 8. You can't get 7.75 or 7.81 shoe sizes. That has to be one of those values. So that's a discrete data, where the actual measurement of your foot is this one. It's continuous. So first thing we're going to do, let's see if we can identify it. The number of songs found on a random selection of MP3 players. Let's say phones. Because, it's 2000, whatever. So this one, could he count this? Always one thing, could he count the number of songs in your phone? Is your phone going to have 31.45 songs? Like, no. It's going to be countable. It's going to be 30 or 40 or 500, whatever you have. So this is discrete. You could count them. You're not going to get half a song. Let's see some more examples. Same idea. The number of page links to a web page, that's also discrete. The number of stations on a cable package. So like if you get channels, right, you're not gonna get half a channel. You're gonna get a countable amount. So that's discrete also. The amount of precipitation in the city. So how much does it rain in a city? That is continuous, right? You're not gonna go. The rain in the city is not gonna be 2 inches and then jump up 3 inches with no in between. There's in between value. It could be anything. So this is continuous. It could fall anywhere in between. The number of cars passing through an intersection in a given time interval. That's all about kind of your reference. Are we talking about, are we counting this the full car? Are we counting partial cars? So I'm going to go either way. This one's actually kind of ambiguous. I'm going to let that one go. Because if you're talking about, you're just counting full cars through, that'd be discrete. But if you're counting like half a car, because in that snapshot you took, and like in that time given interval, then well, I'll say it's continuous. So it all kind of depends on what we're talking about. So let's talk about probability distribution. So this is actually the way we list out our probabilities. So a couple of key things here. Probability in general we talked about before. The max you could do is a 1, right? The max probability is 100%, or 1. And the least probability is 0. Another big idea here is this. The sum of all your probabilities should equal 1. So think about flipping a coin, right? So you have heads and tails. Odds of getting heads is 1/2. Odds of getting tails is 1/2. If you add them up, you get 2/2 or 1. Anytime you have probabilities, when you add them up, you should always get 1. Very, very big idea. The last thing was something we talked about before. There's 2 types of probabilities. Theoretical, that's just based on the mathematics, and experimental, that's based on experiments. You do an experiment, you take the findings, blah, 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 blah. So like real quickly right here, let's do an experimental one. So what happened here is they dropped a batch of paper clips onto a piece of paper. And some of them fell inside the paper, some fell on the paper. And based on this thing here, there's 145 paper clips in total. So my total was 145. And then they said 113 fell completely inside. I call BS. And at 32, only 32 fell on the line. That seems off. Anyway, they want to know, based on this experiment, what's the probability of getting a paper clip that falls inside a square? Well, you can put 1 over total. I'm going to do 113 over 145. Following the line, 32 over 145, right? That's small number total. Based on the experiment, there you go. Example right here. Jose surveyed the length of TV commercials in seconds. Find 3 decimal places experiment probability that randomly chosen TV commercial lasts between 20 and 30 seconds. So first thing I do here, if we can do that, I want one over total, right? I don't have a total right now, so I got to add all these up. So you got 17, 38, 19, and 4. And you get some value. And then 20 over 30 is 38. So 38, whatever that total is. Say the sum of the frequencies. Look at that. Be more than a minute. So here's a minute 60 seconds. So more, that's 4. So 4 over whatever our total is. That's putting some of the frequencies. And then C says between 20 and 59 cents inclusive. So they want you to add these two values up here right there. So that's going to be 57 over the total, whatever the total is. It's not that bad. 57 plus that, 61, 61 plus 17. So about 88. So I can put 88 on all these instead of just like total. And that's the idea. Then from here we could move on. We can talk about how to graph an experimental probability distribution. And all that is, it's a graph that lets you know what's the odds of each thing, right? So all you do is go to your value here. Let's do it here, right? I'll put my on line inside. Then over here you put your marking. So 0, I got all the way to 145. And let's say inside went to 113, so around there. And then on the line is only 32, so that's gonna be like more down here. And there's your probability distribution, right? Just by a quick look at like, okay, that's gonna happen way more often. So look down here, right? Sum of 2 dice. Oh, 7's happen the most. And again, this was an experimental one, so it's not like nice and even. 12 happened more than 11 in this case, right? Because it's based on an experiment, but they did a probability distribution based on that. Then we can do one for theoretically. Theoretically, remember we talked about, is based on this knowledge and logic and mathematics. So look at this problem. We'll do this problem right here. A cart of a dozen eggs contains 8 brown eggs. The rest are white. So here's my dozen eggs. My total is 12. I know 8 of them are brown, and the rest are white. So 4. I did the math. How many white eggs are in the carton? 4. 12 minus 8 is 4. Find the probability that an egg selected at random is in brown. So you go, okay, 1 over total. Again, we didn't do any experiments. We just did the math on it. It's like, okay, there's 12 total. There's 8 brown. So 8 out of 12, or 66%. White, well, there's 4 of those. There's 12, so you get 1/3, 33%. And that's the idea of experimental, right? You do it based on theory. Sorry, theoretical. Do it based on theory. And likewise, we can do the same thing with our probability distribution. We can do the exact same idea. This is 2 dice, right? And you can graph it. Now notice that's nice and symmetric. It's based on mathematics, not an experiment. Okay, next step. Let's talk about expected value. Expected value is another fancy way to saying the mean, or the average, or just what do you expect to happen. So if I roll it down, what do you expect to happen? That's called expected value. Now here's the formula for it. I'm probably going to give you one that says this. That's my fancy E that I selected drawing right there. There we go. Slightly better. And P. And that just says, same thing it says here, right? You get your number and you times it by the probability. That's how you find expected value. Now, number times probability, notice there's an E here. Remember what that means? That means sum. We're going to add them all up. So let's look here. A game show contestant has one spin of the wheel at the right. Find expected value is winning. So let's say, so the idea here is, if you're going to spin this wheel, what do you expect to get on average? On average, what do you expect to get if you spin this wheel? So the way we find it, it's very simple. We're going to find the sum of each value times this probability. So first value, right? Let's start with this, no prize. So that's 0, right? You don't get a win. That's 20% chance of that happening. Plus the next one, 5 grand. 36% chance of that happening. Plus the next one, 10 grand. You have a 22% chance of that happening. Plus 15 grand and 14%. And then finally 25 grand, you have an 8% chance. And we're going to multiply this all together using our calculator, and we'll get an answer. We get $8,100. So now you might wonder, like, wait, how do on average you get 8,000? I can't get 8,000 anywhere, because again, it's on average. Most of the time you're going to get 5 grand. Sometimes you get 0 or 2,000, but on average, if you just average it all up, it would be about 8,000 you would get for each spin. Not bad. So this next one. So this one, the first question is, it's a random variable, right? So here's our variables, here's our probability. So odds of getting 0 is 0.10, odds of getting 1 is 0.3, and so on. First question is find K. Now, if we talk about this a little bit. Remember, your probabilities have to all add up to be 1. If you add all these up, it should equal 1. So that's the first thing we're going to do. Find our K. So we're going to add all these up. And set equal to 1. If we do the math, I think we get 0.15. So that's our K. Now the next question is, it says, what's the odds of getting greater than or equal to 3? Now, key important, it says greater than or equal to 3, so I'm going to go 3 or 4. We're just going to add those two up. So probability of 3 is 0.10. Probability of 4 is 0.15. We just figured that out. So we get 0.25. So we have that. And then finally, it wants to know what's the expected value. So again, we talked about expected value. All you do here is you're going to multiply all these together and add them up. So my expected value is going to be 0 times 0.1 plus 1 times 0.3 plus 2 times 0.45 plus 3 times 0.10 plus 4 times 0.15. If we add them up, we get 2.1. So expected value of this thing is 2.1. So on average, if you did whatever this was, you'd get about 2.1. So again, it's expected value. Just multiply your value times the probability of it and add them all up. If you want the expected value of a single thing, you just look at the probability. If you want to expect the value of a couple things, like what's the odds of getting 1 or 2, you just add them up. This is the same idea. What's the difference here is that they don't give you the probability. Well, how do you do it? You do 1 over total. So if you add all this up, I think you get 5,132. If you add all these up. So the probability of this one would be whatever 5,000 is over 5,132, 100 over 5,132, and so on. And then you just do the exact same thing. We're going to skip the rest of that for now. Same thing here. Let's go to this one real quick. Graph the theoretical probability distribution. So let's do that. We haven't done one of those in a while. Now there's actually two ways to graph it. You can do a chart or you can do a spike graph, what they call a spike graph. Let's do this real quick. So no prize, $0. Let's do this for prize money. And then let's have $5, $10, and $20. And we're gonna go, our max should be 1 because it's all probability, so max you ever hit was 1. Ooh, let's do how am I gonna do this? 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. There you go. Make it kind of works. Anyway, let's do no prize is 84%. So far and away, no prize is the biggest. So let's do a spike graph. I know this. You go 0.84, so around there, and you just go straight down. We call that a spike graph. And then $5, 10, so like right here. $10, 0.05, so that's like less than half, it's like half of that. And then $20 is really small, so it's like a little dot right there. So you can see in this thing, far and away you get no money, no prizes on this one, and the odds go worse and worse. So next question is find the expected value. Okay, so the expected value, we're just going to multiply our prize money by the percentage. So 0 gets to 0.84, $20 gets to 0.01, $10 gets to 0.05, and $5 gets to 0.10. Add this all up. This will be 2 plus 0.5 plus 0.5. Just checking, that's 0.2 actually, sorry. Add that up, you get 1.2. So expected value of playing this raffle, okay, the table shows probably a raffle, 100 tickets sold. So expected value of playing this raffle, you get about $1.20. To what results you found in part B, what can you include about this raffle? Now, let's see. Tickets are sold for $1 each. So, tickets are sold for $1 each. I expect to get $1.25 each. So, it's a pretty good raffle. Like, I would take that raffle. You pay $1, you get you expect to get $1.20. Now, again, most of the time you're not going to get $1, but odds are strong enough that you might get 5 or 10 at some point and make it all worth it. So, this is a good deal for player. Bad deal for dealer. Now, there's actually a thing we call a fair game. And that is when the expected value equals the cost. So this is not a fair game. It actually helps the player because they're going to expect to win more. But if you want to make this a fair game, so like it's fair but involved, whatever the cost is should be the expected value. So to make this fair, the cost should be about $1.20 to play. And that's the idea behind expected value.